Now there's a whole nother category of applications of all this counting stuff that I think you're going to find very interesting. But remember, let's review just a little bit about the counting that we did before. It was pretty simple. It was divided really into two categories of counting. Remember the one where position mattered and the one where position didn't matter. If position matters, for instance in this example, we're going to try and find how many, we did already find how many ways these three people can ride in this two-seater. Now, really matters in this case, you may remember, because it matters whether you're driving or not. We had a possibility where Joe was the driver and Ruth was the rider, or Joe was the driver and Mary was the rider. Okay, that's with Joe. Then we had Ruth as the driver and Joe as the rider. Ruth as the driver and Mary as the rider. Then we had, just to emphasize how much it really matters where you're sitting, we had Mary driving. Mary's 4. And Mary driving with Joe or with Ruth. And in this case, as you can see, position mattered, and we had 3 times 2 ways to do this. We called that a permutation of 3 things taken 2 at a time. And the way to calculate it was just this. Don't forget that 3 minus 2, or 1 factorial, comes out to 1. So we did get the 6, as you can see. Now what happens,
I'm trying to think, but nothing happens,
if position doesn't matter? In this example, you may remember, we had the same 3 people, but this time we were picking up tennis partners.
Excuse me, Professor Brainiac.
And it doesn't matter on a team. There's no position, really. It's just 2 people. For instance, the team of Joe and Ruth is the same as Ruth and Joe. So we have to knock one out. And the team of Ruth and Mary is the same as the team of Mary and Ruth. So we're over-counting, aren't we? Once again, the team of Joe and Mary is the same as Mary and Joe. So we have to wipe one out. So as you can see, we only have 3 possibilities for teams for tennis partners.
Houston, we have a problem.
So we're going to have to do something to our permutation formula so that we can knock out our duplication. And what we ended up doing was dividing by the number of ways that those positions can occur. And we called that added calculation a combination. In this case, a combination of 3 things taken 2 at a time. So if position mattered, we called it a permutation. If position didn't matter, we called it a combination. And in this case, it came out to 3. Typically, the combination comes out to a lower number.
Any of this sinking in, boy?
Okay, the other thing that we covered is if sometimes we're going to have to break a problem into a bunch of little problems. And here's an example that we used. We had a bag that contained 2 purple, 5 green, 6 black, and 4 blue marbles. And we wanted to know in how many ways, another counting problem, without regard to order, so we smelled combination, in how many ways can the 4 marbles be chosen? Well, that's going to be a combination of 17 things taken 4 at a time. Where did the 17 come from? 2 plus 5 plus 6 plus 4. Okay?
now what am I going to do?
Now what if you may remember we threw the little wrench into the problem here. We needed all the marbles to be the same color. Well, what I was trying to demonstrate in this problem was that we can break a problem like this up into a bunch of little problems. How many ways can those 4 marbles be all purple? Well, that can't happen because we only have 2 of them. How many ways can they be all green? Which we have 5 green ones, so that would be a combination of 5 marbles taken 4 at a time, which ends up being 5. How many ways can they be all black? Well, that would be, we have 6 black ones, so that's a combination of 6 marbles taken 4 at a time. We put that into our calculator and get 15. And then a combination for the blues of 4 marbles taken 4 at a time, and that's only going to be 1. Okay, but I'm trying to show you to don't be afraid to break problems up into a lot of littler problems. And of course this one,
How do I do it?
this one comes out to 5 plus 15 plus 1, or 21. Okay, now just in case you think you might have forgotten how to get these numbers on a calculator, I'm going to review very, very quickly. Okay, I'll try and let's get the combination of 6 things taken 4 at a time. Make sure we get this 15. Okay, well, let's see. Let me turn this baby on, and I'll hit the 6. And now I need the NCR, which is a combination. So I go to Math, and I'm going to cursor over to the probability. Now, maybe you're starting to get a flavor why we get the probability menu. So I'll cursor a couple times. And the NCR, you may remember, is number 3. So I'll cursor. I could hit 3 or cursor down to 3. And I'll hit Enter. And it'll say NCR. And then I have to hit the 4. And that's a combination of 6 things taken 4 at a time. I'll hit Enter. And that's where the 15 comes from. Okay? Okay. We've done a lot of counting. And at this point, many students will ask me, why all this counting, for cripe's sake? Well, it brought with it its own problems that we could solve, which we did for homework. But there's, as I said, there's a whole nother category of problems that are going to allow us to do some applications. And that's going to be measuring probabilities. Okay? Now, think about this. Let's do a quick problem and see where counting was involved. Why is flying, and this is true, why is flying in a plane safer than driving? We know all statistics tell us that this is true. How do we know that flying in a plane is safer than driving? Well, it's all relative, isn't it? How many deaths occur to people that are driving versus how many people are drivers? Well, there's a lot of both, isn't there? How many people die in planes? Now, I know you hear about them, but not many do. People die every day on the roads. Many people die every day on the roads, but not many die in planes, or you'd hear about them on the news. And how many people fly every day? All you need to do is go wait in line at an airport and see that millions, perhaps billions, fly every day. Okay, I know the drivers is the same way, but we don't have as many deaths flying as we do driving. Okay, of course, in order to prove this, we would have to count all these numbers, and that's what we do. That's what we use it for in probability. So, in general, if you think about what we just did, the probability of something happening, the probability of an event, we call it. We'll say it's event E. If E is an event in a sample space, we'll talk about that in a second, with N of E. Remember what N of E is? The number of members of a set E. So it has the number of outcomes, and N of S is the number of outcomes in the sample space, which means the number of equally likely outcomes. Then we define the probability of event E. It's denoted P of E, probability of E, is equal to the quotient, the number of ways that E can occur over the number of members in the sample space. Now, this sample space is the set of all possible things that can happen at all, with no limiting restrictions. Typically, E is going to have some limiting restriction. Okay? Another thing we know about probabilities is they're always going to be somewhere between 0 and 1. The highest a probability can be, if we're positive it's going to happen, is 1. If we're positive it isn't going to happen, it's 0. But typically it's going to be somewhere between between 0 and 1. Okay?
Allow me to demonstrate.
Let's try it. Let's take a very simple problem. Let's roll 1 dice.
I know that, dude.
Okay, now the sample space, remember what we said, is the set of all possible outcomes. What is the set of everything that can possibly happen when you roll 1 dice? There it is. There's and 1, you can roll a 2, you can roll a 3, you can roll a 4, you can roll a 5, or you can roll a 6. That's the sample space. Now you have to ask, what is the number of the sample space? How many members does it have? Well, count them. 1, 2, 3, 4, 5. It has 6 members. Okay? So that's the size of the sample space. Now, what is the probability, the P, of getting an even number? By our definition, quite simply, it's the number of ways that can happen over the number of ways in the sample space. Well, how many ways can I get an even number? 1, 2, 3. And how many are in the sample space? 6. So the probability of getting an even number is 3 over 6. Of course, we should reduce and get a half. So we have a half. We knew that already. We have a half chance. But that's the idea. 1 out of 2 chance, if you would. What's the probability of getting a number greater than 2? Well, let's see. Once again, it's the number of members in the event space divided by the number of members in the sample space. How many ways can we get a number greater than 2? 4 ways. And how many are in the sample space? 6 ways. Well, which we got to reduce. So the probability of getting a number bigger than 2 is 2/3. Get the idea?
Do that again.
Okay, let's get a little bit more difficult. Let's consider rolling 2 dice. Now we're going to start to get into some a little bit advanced counting. Okay, if we roll 2 dice, the first dice can give us 6 possibilities. And remember our multiplication principle. The second dice can give us 6 possibilities. So really, how many possibilities can happen total from 2 dice? 36 different things can happen using the multiplication principle that we learned in the counting section. What is the number of ways that a 4 can occur? Well, let's look at it. We could get a 3 and a 1. We can get a 1 and a 3. We can get a 2 and a 2. And that's the only way. So there's 3 ways that a 4 can happen. And our sample space is 36. So the probability of getting a 4 is 3/36, or reduced 1/12. Let's try another one. About a 7, of rolling a 7. Those of you that play craps might know a little bit more about this. Well, how many ways can I get a 7? Get a 6 and a 1, a 1 and a 6, a 5 and a 2, a 2 and a 5, a 4 and a 3, or a 3 and a 4. So that's 6 ways. And of course the sample space has 36 ways. So if we reduce that fraction, the probability of getting a 7 is pretty good. It's 1 out of 6 times. Okay, 7 occurs a lot in craps. 12s don't occur very often, do they? Because the number of ways you can get a 12 is only 1 way. And the sample space is 36. So the probability of getting a 12 is 1 over 36. 1/36. Doesn't happen very often, does it? Now please notice that we used one of the more basic counting theorems, if you would, the multiplication principle. But counting is going to be integral to this. Okay, it's going to be all throughout this probability stuff, because we have to count how many are in the sample space and how many are in the event space. Okay, well, we're going to get a little bit more advanced with our counting here.
Excuse me, Professor Brainiac.
Let's find out what the probability of
You'd like that, wouldn't you, boy?
a 5-card flush hand would be. That would be real nice. I wonder what the probability of getting it, because it usually wins. Well, it's going to be the number of ways I can get a flush over the number of ways I can get 5 cards. Now remember, when we speak of hands, order doesn't count, does it? So we have to use combinations here. Okay, let's start with the sample space. The number of ways I can get 5 cards from a 52 card deck is quite simply a combination of 52 cards taken 5 at a time. Notice it was a combination because order didn't count. Now, of getting a flush, and I say a flush of any suit. If I pick a specific suit, for instance clubs, I have to get all 5 cards from that suit. So I'm talking about a combination of 13 cards, there's only 13 clubs, taken 5 at a time. But I've only accounted for the clubs. Okay, how many suits do I have? Well, I have 4. So I have to take that number and multiply by 4. Okay, now this is the way you could write it on a test, and then, you know, you've shown that you know how to do it. Then and only then do you put it into the calculator. But you do need to write this on a test to show how you got your answer. If we put all this into the calculator, it comes out to, wow, 19 10,000ths. Not a very high number. It is, of course, it's hard to get a flush. Okay. If you get one, I think you probably want to bet on it. Okay, that's about 2 1,000ths, very close to 2 1,000ths. So it's about 1 in 500 hands. Okay, so don't be too hopeful. Now you got to ask: is this the only thing we use probability for gambling? No. It's going to be used a lot in industry. Okay, especially in production. Let's look at this example. We've got 100 calculators in the bookstore. 2 of them are defective. Okay, you've seen things that are broken in various stores. The math department is going to buy 8 for use in the lab. What is the probability in this situation that all 8 are good from those 100? Well, we've got to stick with our definition here. Okay, have some discipline. Don't just jump into 8 100s, because that's not the case. Okay, it's the number of possible good groups of 8 over the number of all groups of 8. Okay, and we're drawing from 100. Remember. Okay, so our sample space is going to be a combination of 100 calculators taken 8 at a time. That includes the goods and the bads. Okay? Now, since we have 2 bad ones, how many good ones do we have? We have 98 good ones. So we're going to take the number of ways we can get good groups, since order doesn't count, remember, too, is going to be a combination of 98 computers, 98 good ones, taken 8 at a time. Okay, and if you would put that into your calculator, you've got a pretty darn good chance, of course notice that it's between 0 and 1, of getting all good ones. What if I asked you to give me the probability that exactly 1 was broken? Well, now we're going to use our combination theory, and we're going to use our multiplication theory. Show you what I mean. We're going to use the same principle. The groups of 8 with 1 broken, we got to calculate, and then of course our sample space is no limiting factors. So let's start. I like to start with the sample space. Gets me thinking. That's not too bad. So it's a combination of 100 things taken 8 at a time. Now we've got to calculate how many ways can we get 1 broken. Well, not that it matters too much, but let's start with in this group we're looking for ways that we can get 1 broken out of the 8. So let's start with the 7 fixed ones, okay, the 7 ones that work. That's going to be a combination of 98, we only have 98 working ones, taken 7 at a time. Now the multiplication principle says I can multiply that by the remaining one, which is going to be drawn from the 2 broken ones at the store. So that'll be a combination of 2 taken 1 at a time. And that all comes out, if you put, I'm not going to take the time to put it into the calculator, comes out to 0.148. Okay, so you have not that good a chance of getting exactly 1 broken. And we haven't accounted for how many that have 2 broken. Okay, probably a lower number also. We're probably in good shape. But you can see where we would use these type of calculations in business, hopefully.
Thank you, sir. May I have another?
Let's try another interesting one. Suppose the school issues you a 4-digit PIN number, and that it's just completely randomly selected by the computer. Some people get interesting pins, some people get 1, 2, 3, 4, some people get 4, 4, 4, 4, etc. Just completely random. I wonder what the probability that your number will begin with a 0. Well, let's calculate. We have to count the number of all pins, and we'll have to count the number that begin with 0. I'm going to use the multiplication principle again here. Okay? The number of all pins, well, we have, here's where order counts. So I'm just going to use the multiplication principle. The first digit, I have a choice of 10 digits, don't I? And the second digit, I have a choice of 10 digits, and on, and so on. So my sample space is 10 times 10 times 10 times 10. Now, let's count the selected event. How many pins begin with 0? Well, for the first number, how many choices do I have? Just one. For all the other numbers, I can have anything else. So that will be 10 times 10 times 10. You get the idea? So what's this? Everything's going to cancel, and I'm going to get a 1/10 chance of beginning with a 0. That seems reasonable because it's 10 digits. Okay? Let's look at it again and think of the probability that no digits are repeated. I wonder what that would be. Well, it's going to be the number of ways we can not repeat the digits and over the total sample space. Sample space was easy. We'll use the same one from the last problem. That's 10 times 10 times 10 times 10. Okay, using the multiplication principle. Now, let's try and calculate how many non-repeat digit pins we have here. The first digit can be anything, it just can't repeat. So that'll be a 10. The second digit can be everything but that one, so I have a choice of 9. The third digit can be everything but the first two, so I have 8. And the fourth digit, so on, can be everything but the first 3. And if we do that calculation, we could have used a permutation of 10 things taken 4 at a time, couldn't we have? It's all a matter of how you want to do it. But you get the idea, and notice that order does count in this case. Comes out to half and half. Just about half and half. Now there's another principle involved with probability that's very important and very useful.
Prepare to be astonished.
Let's demonstrate it, and then I'll tell it to you. I'm going to take 2 dice. I throw the first one, of course, I have 6 possible things that can happen. And the second one has 6 possible things that can happen. So our sample space, when I throw 2 dice, you've seen this before, is going to have 36 possible things. Okay? Now I'm going to quickly rush through all the possible rolls. The number of ways I can get a 2, it's only snake eyes, is 1 way. So the probability of getting a 2 is the 1 over the 36 for the sample space. Okay? There's only 2 ways to get a 3. I don't know if you noticed. A 2 and a 1 and a 1 and a 2. So that's going to be 2 out of 36. Now just for this demonstration, bear with me, I'm going to leave that as 2/36. I wouldn't expect you to do that, but I'm going to leave it there. Just you'll see why in a second. Okay, we're not going to reduce, but normally we would. There's 3 ways to get a 4. A 3 and a 1, a 1 and a 3, or 2 2s. So the probability of getting a 4 is 3/36. 4 ways to get a 5, as you can see. So that's probability is 4/36. Happens to be 5 ways of getting a 6. 3 3, 2 4, 4 2, 1 5, and 5 1. So that's 5/36. 6 ways of getting a 7. Now we're going back down. There's only 5 ways of getting an 8. Look, a 6 and a 2, a 2 and a 6, a 5 and a 3, etc. Okay? 4 ways to get a 9.
Oh, I can't take it anymore.
Bear with me. I'm going to show you something. It's pretty cool. 3 ways to get a 10. 2 ways to get an 11. And, of course, only 1 way to get a 12. 2 6s. Now, big deal. Now, this is all the possible things that can happen, isn't it? You can only get, you can't get a 1, right? You can only get a 2 through a 12 when you roll 2 dice. Now, if we take all those probabilities guess what they add up to? 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 adds up to 36, 36, which is 1. Isn't it? 1. All the possible probabilities in a sample space will always sum to the number 1. So let's use, this is going to be one of our general rules of probability. In any sample space, that as long as there's a finite number of outcomes, and that's basically what we're going to be dealing with, because we wouldn't be able to count them, the following is always true.
That's the fact, Jack.
The probability of any event is going to be some number between 0 and 1. And I say inclusive. It could be 0 or it could be 1. Okay, remember, if it's 0, the probability is not going to happen. We're sure it's not going to happen. And if its probability is 1, we're positive that it's going to happen. But usually it's somewhere between 0 and 1.
Certainly.
The sum of all the probabilities is going to equal 1. And that's going to be useful for calculations later. Okay? And
Well, duh.
the probability of nothing happening is 0. The probability of the empty set is 0. Okay? That's not that useful at this point anyway.
And now, ladies and gentlemen, let's get ready to rumble!
Let's do some real probability. Bring it on, baby. Okay, 3 cards, card hands, are dealt from a 52 card deck. Now these are hands, so that means order doesn't count. The number of queens in each hand is recorded. So what is the sample space, first of all, and what is the probability of each outcome? Let me demonstrate that to you. Well, the set of all possible outcomes is what the sample space is. We're only getting 3 cards. So what is the possible things that can happen here? Well, I can get no queens, I can get 1 queen, I can get 2 queens, or I can get 3 queens. That's all the possible. I can't get 4 queens because I don't have 4 cards. Okay? So my sample space is 0, 1, 2, or 3. Get the idea? Now let's figure out what is the probability of getting no queens from a 52 card deck in 3 card hands. I usually, as I usually do, I'm going to try and figure out the sample space first. It's going to be a combination of 52 cards taken 3 at a time. Okay? Now, we want to, in this example, get no queens. So the numerator can only be picked, there's 4 queens, from the other 48 cards. So we're going to pick a combination of 3 cards from 48 cards. Okay? So the probability of getting no queens is a combination of 48 things taken 3 at a time, over a combination of 52 things taken 3 at a time. Now, let's try and find out the probability of getting 1 queen. Well, I'm going to start with the same sample space. We have to get exactly 1 queen, not at least 1 queen, exactly 1. So, the way we can get 1 queen, first of all, is pick from those 4 queens. So a combination of the 4 queens taken 1 at a time. And then I have to pick my other 2 cards from the remaining 48. And I'll use the multiplication principle. Okay? Now I'm not going to take the time to calculate that, but hopefully you'll see where that came from. I use the combination theory and the multiplication principle here. Okay, we're going to do something very similar to figure out the probability of getting 2 queens. We'll use the same sample space. 3 cards drawn from a 52 card deck. That's a combination of 52 taken 3 at a time. Now, let's produce the 2 queens first. I have 4 possibles in the deck. So it's going to be a combination of 4 queens taken 2 at a time. And how many cards do I have left? I only have 1 card left to draw from my 3 card hand. So that, and I have to draw that from the non-queens. So it'll be a combination of 48 cards taken 1 at a time. And I'll use the multiplication principle there again. Okay? One more. The probability of getting all 3 as queens. Well, I hope you appreciate that. That's not going to happen very often. But we'll use the same sample space in the denominator. Combination of 52 cards taken 3 at a time. Now, how many ways can we get 3 queens? Well, we only have 4 queens, so it's going to be a combination of 4 queens taken 3 at a time. Okay?
I can do that, but I don't want to.
I want you to understand the theory and what can help us get what is the probability of getting at least 1 queen. Now, we did something like this at the beginning of class, and we could kind of manhandle it. At least 1 queen means I get 1, 2, or 3. Okay, and that's an ugly, there's a lot of ugly combinations. I could add that to that. It's a lot of typing in the calculator, isn't it? And add it to that.
What a dumb thing to do. I bet you wouldn't have done anything like this if Mom and Dad were here.
Seems like a smart thing, but I proposed to you that it's not the most efficient way to do this. Because if you consider that all of these have to add up to 1, we want to get the probability of getting at least 1 queen.
Hey, wait just a minute.
We can do it in a much more efficient manner. How about subtract, since they all are supposed to add up to 1, the probability of getting no queens from the number 1. It'll be way less calculations, and we know we'll be right. So consider that. And often you can't even find the probability of something happening, but you can subtract the probability of it not happening from 1 and get the answer. That's going to be a common trick in probabilities, so get used to that.
You have chosen wisely.
That's the way to do it. Now
you listen to me. I want details, and I want them right
I'm going
now.
to ask you to do a histogram. Hopefully I can show you what it is and why it's useful. A histogram is a graph of all these probabilities. It's kind of a bar chart. Now, in this example, there was really 4 different things that could happen, so we need to put all 4 on our chart. Okay? The 0, the 1, the 2, the 3 queens all on the chart. We know the probabilities have got to be between 0 and 1, don't they? Okay, so that's as high as I need to make my graph, and maybe the numbers in between. Okay? Remember, the probabilities for 0 were this calculation, which I'll do it for you, comes out to 0.782. The calculations for 1 queen was this calculation, which trust me if you would, comes out to 0.204. The probability of 2 queens, we're getting less and less here, aren't we? Came out to this one, you may remember, and if I put that into the calculator, it comes out to 0.013. And the probability of getting all 3 queens, it's a teeny number, very teeny number, okay? Now what you're looking at there is a histogram, kind of a graph of all the possible outcomes in a sample space. It's not difficult. Now, I hope you know the answer to this already. What if I took all of them, all 4 of those possibilities, and that's all the ones that exist, and I added them up? I'll stack them for you.
Check that out, huh?
I'll stack them for you. Guess what? Of course it comes out to 1, doesn't it?
Just as I suspected.
Of course it should. All the possible outcomes in a sample space will always equal 1. You'll need to know that.
Think you'll come again.
Let's try another one. We've got 12 toasters at an appliance store. 3 of the 12 are known to be defective. 2 are purchased without regard to order, so we're going to use combination here, okay? We're not going to care about which one we bought first or which one we bought second. Okay? Here again, we're going to ask you what's the sample space going to be? Tell me all the possible things that can happen to you, and what is the probability for each outcome. Okay, well, let's start out finding out what the sample space is. What are all the possible outcomes with no limiting restrictions that can happen when we purchase 2 of these 12 12 toasters. I hope you appreciate we can have none defective, we can have one of our two being defective, or we can have two of our two being defective. Boy, that would be a hugely unlucky situation, but it could happen. Okay? So we have three problems to do here. The probability of none of my toasters being defective is going to be, let's put in our fraction and count, first of all, the sample space. Okay? I've got 12 total toasters, and I'm selecting 2. So it's a combination of 12 toasters taken 2 at a time. Okay? Now, for the selected event, which is no toasters being defective, I only have 10 to select from, right? No, 3 of the 12 are known to be defective, so I only have 9 to select from. So I'm going to select my 2 toasters from 9. So it's a combination of 9 taken 2 at a time. So whatever that comes out to, that's a probability of no defectives. Okay, now the probability of 1 defective will start with the same sample space, 12 toasters taken 2 at a time. Now, let's produce that 1 defective one. And how many defectives do we have? 3 of the 12. So we've got a combination of 3 things taken 1 at a time. We'll use our multiplication principle to multiply for the other toaster, which is taken from the 9 non-defective ones. So we've got multiply by a combination of 9 toasters taken 1 at a time. Get the idea? And finally, our last possibility, the probability of being so unlucky and getting 2 broken toasters. It's going to have the same sample space in the denominator. And we're going to pull those 2. They all have to be broken. So we only have 3 broken ones. So it's going to be a combination of 3 taken 2 at a time. Get the idea?
There's something I have to ask you.
Once again, let's start with a little bit more difficult problem. What is the probability of at least 1 toaster working? Now this isn't going to save me that much work, but I can do it either the hard way by adding the number of no defectives to the number with 1 defective. That's an ugly one too, isn't it? Or you might save yourself a little bit of work by just subtract from 1 the probability of having 2 defective. Okay, that way you'd have at least 1 working. And you have to do way less calculation. It's a little bit easier. Okay, a little bit less typing on the calculator. Okay, make it easy on yourself.
I make this look good.
Let's take a look at a histogram of this one while we're at it. Okay, the sample space has 3 members, 0 defective, 1 defective, and 2 defective. So we're thinking this calculation, trust me, the probability of none defectives comes out to 0.545. The probability of 1 defective, if I put that into the calculator, comes out to 0.409. And the probability of both of them being defective is 0.045. And we know, of course, you already know the secret, that if you add these,
Why does this keep happening to me?
because it's always going to work, all of the probabilities in a sample space are always going to add up to 1. Okay? Very useful. Let's remember that. Okay. Guess whose turn it is to do the homework now?